The history of a modern commercial jet. We are talking about hundreds of thousands of pounds of metal, luggage, and people pushing away from the Earth as if gravity were an elective force. For thousands of years, humans looked at the sky and saw an impenetrable ceiling. Overcoming that physical limit required more than observation. It required translating the fluid motion of birds into rigid, mechanical mathematics. Sir George Cayley identified flight as an argument between four forces: lift pulling up, weight pulling down, thrust pushing forward, and drag holding everything back. Lift must counteract weight, and thrust must overcome drag. If this balance fails, the aircraft ceases to fly. The history of aviation is the history of engineers finding increasingly sophisticated ways to manipulate these four absolute vectors. Mastering this balance was lethal work. Early pioneers tested these equations with their own bodies. Otto Lilienthal proved that controlled gliding was possible, but he died in a crash before he could successfully integrate an engine. The Wright brothers finally solved the equation in 1903. They built a machine that successfully synchronized thrust and lift, achieving the first flight that was both powered and controlled. To understand the scale of this beginning, look at this comparison. The Wright flyer's entire 36-meter journey was so short it would fit entirely inside the passenger cabin of a modern Boeing 747. The first flight lasted only 12 seconds, but it provided the proof that the physical barrier between the ground and the sky could be crossed through engineering. By 1914, the survival requirements of the First World War accelerated the technology. Fragile canvas gliders were engineered into agile, heavy-duty military weapons. Following the war, builders replaced heavy wood and cloth with sleek, riveted aluminum. This gave pilots like Charles Lindbergh and Amelia Earhart the structural integrity needed to survive grueling, multi-day oceanic crossings. This material shift specifically targeted two variables. It lowered the overall weight and reduced the friction of the air, the drag. Because smoother planes required less fuel to push through the air, long-distance flight became profitable. Workhorses like the Douglas DC-3 transformed aviation from a daring feat into a reliable commercial industry. Engineers built stronger, more efficient machines, which made the sky accessible to the general public. But propellers reached a hard physical limit. During the Second World War, the jet engine bypassed this by forcing ignited air out the back of the plane to generate massive thrust. This equation governs the physical reality of jet flight, the lift equation. It calculates lift based on air density, wing area, and velocity. Notice the velocity squared term. Doubling your speed quadruples your lift. Speed became the primary tool for staying airborne. In 1947, Chuck Yeager pushed this velocity variable to the extreme. He piloted a rocket-powered craft through the sound barrier, proving that human-made structures could indeed withstand supersonic forces. By harnessing the exponential math of velocity, aviation moved beyond simple transport, creating a world where no two cities are more than 24 hours apart. For decades, the industry optimized for speed and scale, leading to the Boeing 747, a queen of the skies that could carry hundreds of people across the planet in total comfort. The ultimate pursuit of speed was the Concorde. This supersonic jet could cross the Atlantic in just over 3 hours, traveling faster than the rotation of the Earth. However, the physics of supersonic flight require immense amounts of fuel. The Concorde reached a point where extreme speed was no longer profitable, and the noise pollution from its sonic booms limited where it could fly. Humanity successfully conquered the physics of absolute velocity, but we hit the hard limits of economic and social tolerance. Today, the mechanical puzzle of flight is a solved problem. Crossing an ocean is now a routine event that millions of people take for granted every day. The modern variables have changed. The challenge is no longer how to stay in the air, but how to do so while eliminating the carbon impact on the atmosphere. This is why current engineering is focused on propulsion, using high-density batteries and hydrogen fuel cells to solve the problem of ecological drag. Meanwhile, aerospace companies are applying these same four forces to orbital rockets, blurring the technical line between airplanes and spacecraft. We spent a century refining the balance between weight, lift, thrust, and drag. Every routine takeoff is the outcome of those mastered variables. The physics of the atmosphere are no longer a barrier. They are the foundation for whatever we build next.